We can transform proof of existence of computation. Yesterday there were two parts. First he was doing right. After that he used the side thrust. Yeah, that's the point. Yeah, that's the point. So there was like S1 express. Not for that one. We have PN. Then like for PN. Welcome everyone for the second session of second day. So Matthias Reisner will continue his talk for the second talk on recent advances in random polytopes.
Thank you very much. Yeah, I will continue, and the talk today is more a survey talk about more recent developments, and I will point out two subjects which I find of interest. Okay, let's start. First of all, the setting is the same as yesterday. I start with a convex set K, but now not in the planar case, but in general dimension RD. I assume that the volume of this convex set is equal to 1. And then I choose random points according to Lebesgue measure, so uniformly distributed random points. These are the red points in my picture. And then I take the convex hull of these points. And this gives me a polytope, because I'm in general dimension now. It's not only a polygon, but a polytope. It has some vertices, it has some edges, and in higher dimensions, it has faces and facets, and clearly it has a certain volume. And if the number of points is large, this was already pointed out yesterday, then Pn is very close to K. So here in between, this is not much difference. And we are interested in the small difference between the volume of Pn and the volume of K. So these are the functionals which are of interest, and there are now some additional functionals which occur here. It's not only the volume, but these are the intrinsic volumes. These are the surface area Vd minus 1 up to V1. the intrinsic volumes some of them have a very nice geometric meaning, but in general, it's difficult to understand the geometric meaning of the intrinsic volumes. I will shortly define them because it's not clear to me whether they have already been defined. So one possibility is you take a convex set K, and then you add a small ball or a large ball of radius S, and you compute the volume of this. And then it turns out that the volume is a polynomial in S. This is somehow surprising. This is Steiner's formula, and the coefficients in this polynomial, they define the intrinsic volumes. Okay, this is more or less a purely analytic geometric approach. And the second possibility to define these intrinsic volumes is the following. You start with your set K here, and now you project your set K onto an I-dimensional plane L. So the projection gives you then an I-dimensional convex set. It's just a shadow of K in this direction. And then you measure the I-dimensional volume of this I-dimensional shadow. And the mean shadow volume, this is the ith intrinsic volume. So this is somehow I would say, the most nice geometric interpretation of the ith intrinsic volumes as the mean shadow size. So this is Kubota's formula, and these are the two possibilities to define ith intrinsic volumes in a nice way. So for a moment, I have to do something. So that's, yeah. Okay, so let's continue. First, mean values. This is something we already did yesterday. We started yesterday with computing the expected number of vertices and edges, and it turned out this was n to the power 1/3 times a constant. And here I have written the constant explicitly. The explicit constant is some kind of omega-2 of k. I will define it in a moment, but you already know this. And then we have yesterday already computed by Efron's equality that then volume, so if I is equal to D here, then it's just a two-dimensional volume, so the area, how this behaves, and this was n to the power -2/3. So these are the results of yesterday, and I make them more precise by telling you what these omegas which occur here are, and they are just, so omega d is always the affine surface area, and this was introduced already by Elisabeth, so you understand how this affine surface area looks like. It's an integral over the curvature, and this affine surface area can in our context be slightly generalized to some kind of ith curvature integral. This is not a affine invariant. This is something different. Here you take some curvature functional and modify this affine surface area by this, and this is the outcome for the ith intrinsic volume. And so the main point is, if the convex body is smooth like a ball, then this is always the same. N to the power d minus 1/d plus 1 and n to the power -2/d plus 1. So the first thing, it holds for the number of edges, vertices, facets, and all faces. So it's independent which of the face dimensions you are counting. And for the ith intrinsic volume, the order is always n to the power -2/d plus 1, independent which of the intrinsic volumes are interested in. So it's the same for the volume and for the surface area and also for the mean width and everything in between. And these results have been proved in a series of papers over the last 60 years. And the contributions were more step by step. So in the smooth case, we really understand how this asymptotic behavior of these functionals looks like. And the method is more or less what I presented yesterday in the most simple case. You're really looking at caps and what the volume of caps is, and then you plug things together. But in higher dimensions, that's much more complicated, plugging things together. Okay, but this was the smooth case. And then, so if the underlying set here, so to say your mother body, if this is smooth like a ball, and things change. If you don't have a smooth body, but say a polytope. So for a smooth body, what you do is, this is the picture of yesterday, you cut off a cap here. And the main point was that such a cap looks the same wherever you do it. So if you cut off a cap here, then more or less up to an affine transformation, it looks the same at this cap. This makes things simple. All caps look more or less more or less the same. And this is different if you're interested in polytope case. So if your motherboard is a polytope and you cut off a cap, so this is a polytope here, and you cut off a cap, then it looks, in most cases, if the cap is more like this thing here, you have one vertex here, which is cut off, and then you have a small simplex, which is cut off by this cap. But it could look more complicated like this thing. This is a tiny cap, but it cuts off two vertices. And you can imagine in higher dimensions, it's possible to cut off several vertices with a very tiny cap. And you have to take care of all of these strange possibilities to have a tiny cap which cuts off several vertices. This makes things for the polytopal case much more complicated. And this is maybe the point to make an advertisement of Carsten Schütz's talk. He will talk about polytopes, random polytopes in polytopes. And this is a difficult or more difficult thing because you have to take care of all these combinatorial properties that small caps can cut off several vertices. So this is more complicated, and this led to the consequence was that things which have been proven for smooth motherbodies were earlier or more easily than things for polytopes, which were much later somehow. We nearly understand now what's going on for polytopes. We don't have a complete picture now, but we understand how the F vector looks like. And again, it turns out that this F vector, so all facet numbers behave like logarithm to the d-1 of n. And then there's something where it depends on the convex polytope k itself, and this is T of k is the number of towers or chains of k. So what you're doing, if you want to do define T of k, you have a polytope. So this is the mother polytope here. And what you do is you start with an arbitrary vertex. So for example, you start with this vertex, then you continue with an arbitrary edge. This is this thing here, and then you continue with the next high dimensional thing. In our case, this would be already the whole polygon itself. And this is what you do in arbitrary dimensions. You count how many possibilities are there to start with a vertex, continue with an edge, and two-dimensional phase, a three-dimensional phase, and so on. So you lift all the dimensions, and then you count all these possibilities. And this is T of k, the number of chains or the towers of k. And the same formula more or less holds true if you're interested in the volume here. Then it's n to the power -1. This comes from the Ephron identity times again this logarithmic factor. And here you see for the smooth case we had a power of n to the power 1/3 or -2/3. And now in the polytopal case there's a logarithmic factor occurring, and this shows that things are more complicated in the polytopal case. So here's only the formula for the volume. The formula for the first intrinsic volume is also known. This is due to Schneider, but the general case here, this is still open. And this is maybe a surprise that also this is a classical question. We are not able to compute the differences of the intrinsic volumes. We do not know. There's a conjecture that it should look like that. So the logarithmic factor here, this only occurs for the volume, but already for the surface area, the conjecture is it should be a power of n, but we do not know. This is still missing. Okay, this is what I wanted to say about the expectation, but now there are some properties of expectations which I find interesting. And these are monotonicity properties. Is it true that, and I've here made a list of 3 properties. I have a small body K, and I choose a random polytope inside. And then I have a larger body L, which contains K. And then compute a random polytope inside K. So this is something like here. And then I have a random polytope inside L. It should be green. Something like this. So you have random polygons in the larger and in the smaller set. And the question is it true that the random polytope in the smaller set is always smaller than the random polytope in the larger set? So if you increase the set, your random polytope should increase in the mean. This is a very natural conjecture, in my opinion, and the question is whether this is true. Yeah, increasing the set increases the random polytope. The second question is, let the convex set K be fixed, but increase the number of points. So from n to n plus 1. This should also increase the random polytope. And the third question is, what happens if you increase the number of random points? Will this increase the number of faces? So if you plug in more random points, will this increase the number of vertices, the number of edges? These are monotonicity properties which are of interest. And there's one thing which is, say, immediate. If you have n random points and you increase it to n plus 1 random points, then it's quite clear. You plug in one additional point, either nothing happens because this additional point is inside, then Pn and Pn plus 1 is the same, or you get something additional, you gain additional volume. So you have here your original random polytope. If your additional point is inside, nothing happens. And if the additional point is outside, then Pn is increasing to Pn plus 1. That's quite clear. So you have a certain set inclusion here. And this set inclusion clearly increases all the intrinsic volumes, and it also increases the expected intrinsic volume. So this thing here, this is clear. This monotonicity property is really elementary. Okay, let's start with the first non-trivial monotonicity property. This is the property here, and the question is whether this monotonicity is true. And say for the one-dimensional case, this is a trivial computation. Really trivial, and you see immediately that this is monotone increasing in the set. So if you increase the set in the one-dimensional case, this means you increase your interval, then the length of the random polygon is increasing, or the random line segment. In the two-dimensional case, you have to compute this, and yes, you can compute this, and it's not too difficult, and you can just easily check that the monotonicity property holds. Increasing your set increases also the random polytope. And then the three-dimensional case turns out to be complicated. This is not trivial. And then to my big surprise, Louis Rademacher some years ago computed the four-dimensional case, and it turned out that in dimension 4, this is wrong. So in dimension 4, there are cases where you start with a small set, you increase your set to a bigger set, but your random polytope is decreasing in the same set. And you have to, yeah.
So in the d equals to 2 case, if
yeah, in the
yes, so d equal to 2 case. So last day you said when you take a cap, so you make sure that the vertices of the random polytope are close to the boundary. So you use some floating body kind of a diagram to show that also. So d equals to 2 case is the approach kind of similar? Like if the k is smaller and inside, very much inside L, then you can probably say with high probability the random polytope that is inside L that contains K, and therefore this kind of monotonicity property holds.
My conjecture would be yes. If you have a large number of points, then the monotonicity property should hold. Yeah. So the counter example is for d plus 1 points, which is a small number of points. Yeah. What happens in higher, if you have many points inside, it's a good question. That's open, I would say. It would be nice to have something like a threshold. Yeah. If you have sufficiently many points, then it's monotone with a certain respect. Yeah. This is open. So the first question or the first feeling is, independently of how many points you plug in the set, as soon as you increase the set, the random polytope must increase. This would be the natural feeling. And that there's at least one counterexample is very surprising. And in, say, dimension 4, this counterexample is due to Louis Rademacher. I will shortly explain how the counterexample looks like. And this only works for a random simplex. So only d plus 1 points. So what happens if you have more points inside is a good question. Yeah. Yeah, thanks. Okay, so the counterexample is the following. Take a half ball and then plug a small cone onto the flat part of the half ball. Yeah? This is the cone here. And then you take this apex and you cut off this apex, but just with a tiny cut off. So something like this. Yeah? And now you compare these two bodies. So your larger body is this thing here, and your smaller body is the body where only this tiny apex is cut off. Yeah? And the only difference between these two sets is just this cap which is cut off here. So the remaining thing here, this is the missing part. And if you compare the random polytopes which may occur in K and in L, then the only difference are those polytopes where at least one random point is here. All others are more or less the same. So without going too much into detail, what you have to compare are those random polytopes where all random points are here inside floating. So in the I think this thing here. And then you compare to where one point is here. So you take this point here and you shift it into this apex. And the question is whether this increases the volume of the random polytope. Taking one vertex here and shifting it into this apex. So and intuitively, this must increase the volume of the random polytope. Now let's make this cone, which is onto the flat part of the half pole, very, very tiny. Then at the very end, in the limit, you say you have here points, random points inside. And now you take one of these random points and you shift it into the center. And this is what you compare. You have d+1 random points freely floating. You have d points floating, and one point is here in the center. And the conjecture would be if I take one of these points and shift it into the center, then this should increase the random polytope. And what Louis Rademacher proves, this is wrong. In general, you decrease the volume here. That's a surprise. At least for me, it was a surprise when I saw it for the first time. Yeah. And what you have to do is really, you have to explicitly compute this expected volume and this expected volume. This expected volume, this is more or less known how to do this, and this expected volume here, this is a difficult task. And this is the work of Louis Rademacher, that he was able to say, give a good approximation of the difficult thing here and to prove that this behaves in the wrong direction or in the intuitively wrong direction. So this was the 4-dimensional and high-dimensional case. So for the dimension d greater or equal 4, this monotonicity property was wrong. And then that case d equal to 3 was missing. The method of Louis Rademacher did not work in dimension 3. In dimension 3, you just get equality for both cases. There's a conjecture that even there, the half sphere is a good example, but the method does not work. And the second possibility for a good, say, underlying convex set, which could disprove monotonicity, was the tetrahedron, the 3-dimensional tetrahedron. So the question is, can we prove something about the 3-dimensional tetrahedron? And so let's have a look at the results which are available. And so in dimension 2, there are several explicit results available. In dimension 3 and higher, the number of results, explicit results, this is much more rare. So in arbitrary dimension, we only know what's going on for the ball. There you can really compute things, but not for the half ball. This makes the things very complicated. Yeah? And this is where Louis Rademacher had to work to get some approximation for the half ball. But what we have also in dimension 3 is the 3-dimensional simplex. Yeah, the formula for the 3-dimensional simplex is complicated, but at least we can compute it. And the outcome for the 3-dimensional tetrahedron is given here. So this is something which we know. So the right-hand side is known. What is not known is the following. So in the 3-dimensional tetrahedron case, we have something like this, and then you again have somewhere a center, say here in the center, and you have to compute the convex hull of 3 random points and this center. And this here is open. And you have to do something for this thing here, for the random polytope where one of the points is in the center of one facet. What is the volume of a tetrahedron? This is well known. This comes from linear algebra. You get the volume of a tetrahedron, which is spanned by three vectors by just taking the determinant. Determinant is just the volume of the spent parallelotope, or if you normalize it in the right way, you get the volume of a tetrahedron. So this would be a possibility to compute this. And the determinant, this is something which is nice. So the determinant here, this is nice. And nice means this is a polynomial, a determinant in the coordinates. And you could take, in the three-dimensional case, just take this polynomial, plug it into your favorite software program, and then you just integrate it. The disadvantage here is that you have the absolute value here. And the absolute value of a polynomial, this is something you cannot integrate. To get rid of this absolute value, what we do is we just take an even power. Because if we take an even power, this would be simple. Then the absolute value just vanishes. And then you have a nice polynomial, you take the square or fourth power of that, then you integrate it. This can be done using software programs. Yeah? So what we can do is, we can do all even powers, but the power 1, that's impossible. We cannot do that. And then we took a trick from numerical analysis. And the trick is, there's a polynomial of, say, degree 13, and 13 turns out to be sufficient for our purposes, which is larger than the absolute value of x, but is very close. So we approximate the absolute value of x by a polynomial of even powers as good as possible. And the even powers, this is something we can deal with. So the point is, we are having here the absolute value of the determinant, and we approximate it by the determinant to the power 2i. And this thing here, this can be done, and this thing here, this is impossible. But if we can do the even powers, then we just get something, okay, that's not very, I wouldn't have a good guess why this number here occurs, but at the very end, it turns out that's really the thing we need. This very nasty rational number, this is really, in fact, smaller than what's happening on the right-hand side here. Yeah? And this disproves the monotonicity property in dimension 3. Yeah? Without being able to really say what this is, there's a method from numerical analysis that we can explicitly disprove that this monotonicity property holds in dimension 3. Okay, so this small, strange detour, this proves monotonicity property in dimension 3. So in dimension 1 and 2, we have this very natural monotonicity property, but starting with dimension 3, it's strong. So it's not monotone in general. Why have people been interested in this? And there was a question which came from, say, geometric analysis. There's the well-known slicing problem. You have a look at all convex sets of volume 1 in dimension D, and you are looking for the maximal intersection with a hyperplane. And if the volume is equal to 1 here, then the conjecture is the maximal intersection cannot be too small. Each convex set of volume 1 must have a hyperplane intersection which has a certain size. Even if the dimension tends to infinity, this should not tend to 0. This is a really well-known problem in geometric analysis, and there was, say, a long-standing result by Bourgain and Paoris. They proved, so first Bourgain for symmetric case and Paoris for the non-symmetric case or for the general case, that this constant C, they didn't have a lower bound which is independent of the dimension, but they had a lower bound which depended on the dimension in the fourth root of d times logarithm of d. And then Klartak was able to remove the logarithmic term. And then very recently, so this was the best thing here standing for decades, I think. And then very recently, there was a breakthrough by Chen. he proved that this is more or less something like a logarithmic term, and the best known bound at the moment is due to Klartak and Lehek, and they could prove that at the moment best bound is a constant divided by the fourth power of the logarithm of the dimension. So it's close to a constant in the dimension, but it's still not totally solved. Okay, so this is one of the serious major problems in geometric analysis, and the connection is a remark by Mark Meckes that if a monotonicity property holds for the simplex case, d plus 1 random points, then it would prove the slicing problem or slicing conjecture. And so it's not a surprise that if this would have been true, the proof should have been very, very difficult, maybe. And disproving the monotonicity property tells us that this is not the way to attack the slicing problem. Yeah, so the monotonicity sadly does not hold. But this was somehow the motivation for being interested in this monotonicity property. Okay, so we have disproved the first. What is open is if one is interested in the ith intrinsic volume. So for example, surface area is something which is open. We have the third monotonicity property holds, this holds was trivial. And then the last monotonicity property, what happens for the number of edges, vertices, faces, facets? If I increase the number of points from n to n plus 1, does the number of vertices increase? And it is quite clear that this is not true in general. So if this is your random polytope somehow, and you add one random point here, then even this picture you see, you had before this 1, 2, 3, 4, 5, 6 vertices. You added this new vertex here, and then you only end up with 5 vertices. So the monotonicity, if it holds, it only holds in the mean as a mean value. The question is whether the mean value is increasing. If you have a look at smooth convex sets, then the expected number, say, of vertices was a power of n, and for polytopes, it was a logarithm of n. And there's a result due to Imre Barani that for typical convex bodies, the expectation fluctuates between the polytopal and the smooth case, if n is increasing. So the picture is something like this. Here you have the smooth case. Here you have the polytopal case. Here n is increasing. And it fluctuates. It's nearly like a smooth. Then you increase n, then it nearly behaves like a polytopal case. It nearly is like a smooth case. It nearly is like the. So this is the theorem of Imre Barani. If n is increasing, the typical convex body fluctuates between a smooth and a polytopal behavior. And this at least makes a huge question mark whether your red curve is all the time increasing, or whether it could also be possible that it's decreasing in between from the smooth to the polytopal case. Yeah, but clearly the curve could also look like that. You are close to the smooth case, and then you have something like a line segment which is nearly tangent to the polytopal case, and then continues like going back to the smooth case. This could also happen. Yeah, but at least there is a question mark whether the monotonicity is trivial. And the only case where we really do know the monotonicity here is the planar case. There we have a very explicit formula for the expected number of vertices and edges with this. And therefore, one can prove monotonicity, but the general case is widely open. So we know it for smooth convex bodies. There it's clear. There one can prove that. We know it for Gaussian polytopes, we know it for beta polytopes, for certain kinds of random polytopes, but the general case is open. We do not know the monotonicity property in the general case. So some cases we know, the general case is something which is still open. Yeah.
Matthias,
yeah.
So what do you mean by typical convex body? Is it some probability?
So there are smooth convex bodies and there are polytopes, but there are many convex bodies which are neither smooth, C2 boundary, nor polytopes. And the general case in between. This is the typical behavior, and this can be made precise using Baire categories. And most convex bodies are somewhere in between. And most of these bodies which are somewhere in between, they behave sometimes like a smooth convex body and sometimes like a polytope. Yeah.
But then the figure you showed, doesn't it show it's not monotone because there was the fluctuation says there is no monotonicity in those cases, or
That's unclear. So either the behavior is like this picture, so that it's not monotone, or the behavior is like this, then it's monotone.
okay.
Yeah, so both could happen. It's unclear what's really going on. But at least, say this picture here, so this makes a question mark about the monotonicity. If you know it fluctuates between a power and a logarithmic curve, which are far away for a large n, then it's unclear what's going on. Yeah. Therefore, the general case is here still open. We do not know. Okay, some open questions to this first part of my talk. What is open is the intrinsic volume for the polytopes is something, the expected intrinsic volume for polytopes, which we do not know. The question whether the expected intrinsic volume is monotone with respect to set inclusion. So for the volume case, we know that's wrong. But in the intrinsic volume case, this is open. The question whether the number of vertices is monotone in n, that's my last question. And then I want to mention two more things which I didn't mention up to now. So if we replace the Euclidean case, the underlying case, by the spherical or hyperbolic case, this has been of recent interest. Computing expected volumes, expected number of vertices for random polytopes in the spherical and hyperbolic case, and several people have contributed to this question in the last years. And this is somehow also connected to the floating body approach, which, say, in the original question was a Euclidean question. Now people have started to investigate this in the spherical and hyperbolic case, and maybe Elisabeth has said something about that. But this is an interesting question to generalize this to spherical and hyperbolic case. And then clearly the next step would be to replace RD by the complex case. And there has been a very recent first step by Atreya, Gupta, and Yogeshwaran. But I think the most difficult thing in this case here is that we do not really good understand what convex means or convex hull is. So what convex and convex hull means in the spherical and hyperbolic case, this is clear, but the definition of convex and convex hull is much more complex in the complex case. And there's a first step, which is very interesting, and well, there should be next step, going in the complex case to random polytopes. Okay, so this was the first part where I dealt with expectations. Are there some questions?
The monotonicity of the lower intrinsic volumes, do they have corresponding relation to some suitable slicing problem? Is there
I haven't seen something like this. Yeah, good question. I haven't seen something like that. Yeah, for the volume case, I know that there is a connection. Yeah, good question. It's unclear to me. Okay, thanks. Then I will continue. And the second part is again, like yesterday, about the distributional limit behavior. So I'm interested in variances and central limit theorems. And say this is something which we computed already yesterday. We computed more or less, or I gave a hint how to compute what's going on for the variance. So the expectation is something like n to the power 1/3 in the smooth case. And then it turned out that the variance was of the same order. And then I told you we have a lower bound, which is also of the same order for the circle. This is what I told you yesterday. And this is true in general. So in general, if you have a smooth body or a polytope, then we can bound the variance by expectations. And this is also true for the volume. I just didn't mention it here. Yeah. It would be really nice to have this in the general case. So the question is whether this also holds true for general convex bodies, neither smooth nor polytope. And this is an open question. Apart in dimension 2. In dimension 2, Parton could prove, say, 10, 15 years ago, that in the planar case, this always holds. And there was a very nice compactness trick to prove this in the planar case, and this trick does not work in dimension 3 or higher. So that general case here is still open. But at least for the smooth case, for the polytopic case, we know the order of the variance. And then much more recently, this was also a question yesterday, for the expectation, we have really the asymptotic behavior. And for the variance, we only know the order of magnitude. Whether we can make this more precise, computing the asymptotic behavior of the variance, and this is very recent work by Pierre Kalk and Joe Jukic, they could prove in the smooth and in the polytopic case, the precise asymptotics. But only here, they have to assume that the polytope is simple. And this is again due to this difficult combinatorial behavior. If you cut off small caps for polytopes, then that's a difficult combinatorial thing. And therefore, they could only prove this for simple polytopes. Yeah, but at least we have first asymptotic results for the variances. Okay, and the next step is if you know the variance that you prove central limit theorems, and this is something where say in the last
the constant omega k is same as that in the expectation, or is it?
So this omega is again the affine surface area here, and this T of P is again the number of towers or chains of K. So the constant here is different.
Okay.
So the constant is not the same as for the expectation, but the affine surface area is the same.
Oh, okay. So only the dimensional constant changes between the variance and expectation.
Yeah. So the constants they differ, otherwise they are the same. Yeah. And so if you know the variance, then you really can start to attack central limit theorems. This is the next step. And this has been done in the last years. And a large number of people contributed to this question, proving central limit theorems. So we know at the moment central limit theorems for all numbers of faces and for all intrinsic volumes in a smooth case. So if K is a smooth convex body, then we have central limit theorems for everything, all functionals we're interested in. And we also have, if K is a polytope, we have central limit theorems for all L-dimensional phase numbers and for the volume. So what is open here, if it's a polytope, then the general intrinsic volume case is open. And this is maybe not a surprise, because for the polytopal case, we even cannot say something about the expectation of the intrinsic volumes. So we are far off knowing how the variance behaves and how whether there's a central limit theorem. So in the polytopal case, there's again, it's a more difficult question again. Yeah. These theorems have been proved using Stein's method, and Stein's method comes in most cases with an error term. So we get a quantitative central limit theorem. And I want to point out what was going on here in the last years. So say for the volume case, and if K is smooth, then there were central limit theorems, and we could give an estimate for the difference between the distribution function of the normal distribution. So this is the normal distribution. And this is the normalized or standardized distribution of the volume difference. And what you expect of on the right-hand side is something like the variance to the power -1. This here would be optimal, variance to the power -1/2. And then we get here an additional error term. And this comes from the floating body approach we are using. If you use the floating body approach, then you can't do better. And then what I have presented you yesterday was an approach to attack a central limit theorem just using this stabilizing functional and the score function approach. And this new approach, going back to Lachesserie and Schulte and Jukic, this leads to a central limit theorem where you can really remove this logarithmic factor and you get an optimal CLT. This is the very recent approach, the optimal approach, and we cannot do better. This is the optimal thing you can achieve here. So if K is a smooth convex body, then at the moment there are really things available, the stabilizing functionals and score functionals, which give you optimal results for central limit theorems. If K is a polytope, so this is for smooth case here. If the underlying mother body is a polytope itself, then again the situation is much more complicated. Here, this is again what we want to have. This is the variance of f naught to the power -1/2. So this would be the optimal thing. And again, we get here something which comes from the floating body approach, which is an additional log-log error term. And it would be good to get rid of this additional log-log error term and you get the optimal error term. And in the planar case, we can do that. This is again very recent work with Anna Gusakova and Christoph Thiele, but only in the planar case. And this does not use some stabilizing score functionals. This is some kind of detour from to convex random chains. And so this is very different. It only works in the planar case. Yeah. So in the general case, it's open how to get optimal central limit theorems. Okay, so open questions for this distributional approach is we want for general convex bodies a variance bound, say, for the number of faces. For smooth, we know. For polytopes, we have that. For general case, we only have it in the planar case. And it would be nice if we have such a bound, then to get a CLT, a central limit theorem, also for general convex sets, not only for smoother polytopes. This would be interesting open questions in this field. Okay, this was the second part. Are there some questions to variances and central limit theorems? If not, then I have a third part, which again is something which is very recent and I find very interesting. And this is my last part, and it concerns order statistics. Order statistics is something which you know from your elementary statistics or probability course. You have random points somewhere. So you have points chosen. This is x1, this is x2, this is x3, this is x4, and you continue by that. So you have random points on a line. And what you do next is you order them by size or by x1 is the smallest, x2 is the next one, x3 the next one, up to xn. So that you have always something like this. This is the order statistics. Taking random points, and then you take the order in which they occur. And this is important because then you know this is the smallest point, this is the largest point, these are the extreme points. So the extreme points are x1 and x8 in my picture. And if you're in statistics and you want to estimate something like, say, the mean value, then in many cases, if there's an outlier which occurs due to some reason, then you would expect the outlier to be among the extreme points. So you would remove the extreme points in statistics in many cases, remove the extreme points, and then estimate the mean value without the extreme points, which means without the outliers. This makes the statistics more robust. So detecting extreme points is an important tool in statistics. So what is going on? What is order statistics in higher dimensions? So let's have something like this. I'm in a higher dimension, I have random points. I'm looking for the extreme points. Clearly the extreme point is something, say, maybe this is the most left point and this is the most right point. These are the extreme points. But these are only the extreme points if you look in this direction. If you look in this direction, then the extreme points are maybe this point here and this point here. And now if you think about extreme points in higher dimensions, what you would do is you collect all the directions here and look for all extreme points in all directions. And for this direction, maybe it's this point, and for this direction, it's maybe this point. And you see, these are the extreme points for some of the directions. Yeah? These are the vertices of the convex hull. So if you're interested in extreme points, then you are interested in the convex hull. And if you want to remove outliers, you would remove these extreme points, the first convex hull. And then you would try to, say, compute the mean value in higher dimensions or something else. Yeah? Now let's continue with that. so this is the first order statistic somehow. The convex hull is the other extreme points. And if we go back to the order statistics, so what we did here is we had x1, then the next step was x2, the next step was x3. Can we continue in the same sense in this? And if we continue, we remove these extreme points and take again the convex hull. Then we remove the second and get the third convex hull. And this is what is called convex hull peeling. This is the order statistics in higher dimension. I start with the most extreme points. I continue with the next most extreme points, like this convex hull peeling or onion peeling, some people call that. Yeah. And if you think about this order statistics, then suddenly a large number of questions arise. Clearly, the first question is how many extreme points are there and how many second extreme points are there? And how many layers are there? So in my picture here, you have 3 layers. How many layers will occur? Yeah? And maybe the most natural way to attack this question is to say, okay, I have a certain region here, which is between my extreme points and my set K itself. And I give this the number 0. All points x here in between, so if x is here, then I say ln of x is equal to 0 because it is not in one of these extreme hulls. And then I have those points which are in the convex hull Pn1 in my first convex hull. So if x is here, ln von x is equal to 1. And this is the point, these are the points which are in the second convex hull. So ln of x is equal to 2 here, and in here in between it would be 3. So for each point x in my set K, I map it to that number, which is the convex hull peeling number there. And then the number of layers is just the maximum. So the maximum points are here inside, they get the value 3. So this is the maximum, and 3 is the number of layers in my picture. Yeah. So I map all the points here. I map these points, these points here get number 0, these points here get number 1, these points get number 2, and these points here get number 3. And 3 is the maximal number, so that's the number of layers here. And I want to understand this picture. Yeah, this would tell me somehow how this order statistics behaves. A first question is how many vertices are on each of these layers. So if you want to remove the extreme points, how many points do you have to remove? Yeah. So for each layer, we want to know how many vertices, how many edges, how many faces, how many facets does this layer has. What is the volume of each layer? It's quite clear. The volume of each layer is decreasing. The first layer has the largest volume. Then there's the second layer, which has smaller volume. The third layer has less volume again, and so on. So can we say something about the volume of the layers? And then clearly the number of layers is of interest. So what we expect, and naive approach to this question would be, we start with the first layer. This is the ordinary convex hull. This is something which we know. We know this behaves like, say, if K is smooth, like in my picture here, then we know this is the affine surface area. There's a constant in front, and this is n to the power d minus 1. So this is something which we know, the first layer. Yeah? And now let's assume we're interested in the second layer here. What do we have? We have a first layer. This is a polytope. Yeah. In this polytope, which is the first layer, we have random points inside. And we are asking the question, I have random points inside this polytope. I take the convex hull, which is Pn2 here. How many vertices does this convex hull have? So expected number of vertices in a polytope, and the polytope is Pn1. And the expected number of vertices in a polytope, this is well known. This is a constant times these towers times a logarithmic factor. This would be the naive approach. We take the result for the polytopal case, constant, towers, logarithmic. And we have to compute the towers of this polytope Pn1. But the towers of Pn1, this is well known. This is just here. Yeah, the expected number of vertices, this is the same as the expected number of edges. So this is what we know. So we know that this is precisely this. Yeah. So we plug this in. This would be the naive approach. We get something like the towers is n to the power d minus 1 over d plus 1 times the logarithmic factor. This is what, yeah. Okay, sorry, I thought it was a question. So this would be the naive approach. And then Pierre Kalke and Quian.
Yes, I can
Yeah.
just go back one page. So what the second number is bigger?
Yes, but sorry, the constant, it should be a C prime. The constant can be different.
So because the
Maybe.
second number should be smaller, right?
Why? So the volume is decreasing, but the number of vertices, this is an open question. It could well increase.
But you have fewer numbers. You have fewer points.
Yes, yes. Sorry. Here it should be, no, that's correct. But here it should, more precise would be n minus n to the power d minus 1 over d plus 1. Yeah?
Okay, yeah.
Instead of n here. But asymptotically, that's the same.
Okay,
Yeah?
Yes.
And ad hoc, there's no reason why it should be decreasing the number of vertices. It could well be that you start with something like this, and then you get something like this, very close to this, other more vertices occur. Yeah?
Yeah.
So at least for me, it's not clear. Yeah. Okay, and the main point by this result of Kalke and Quian was, okay, only for the ball case, but it should also hold in smooth case, you always have this power of m. There's no logarithmic term occurring. Yeah, so they could prove that this logarithmic term here, it does not occur somehow. If you fix k and you say you have a look at the first 100 layers, then the first 100 layers, all of them behave in the same way, apart from the constant here. This constant is different for each layer. Yeah, and all of them behave like the surrounding mother body is a smooth convex set. So that there's a polytopal shape, this does somehow play no role. Yeah. And they could even prove not only expectations, but variances and central limit theorems. Maybe there was already a hint that this logarithmic term does not occur. And this is due to a theorem by Dalal. And this is a very nice theorem. I like it a lot. You count, ln is the number of layers. So you count how many layers occur. My picture, we have 3 layers. And you start with an arbitrary convex set, polytope, smooth, or general, doesn't matter. So it's for arbitrary convex sets. And then you start with this convex hull peeling procedure and you count how many layers are there. And he could prove that you always get n to the power 2 over d plus 1 layers, independently whether you start with a simplex or with a ball or something else. Always n to the power 2 over d plus 1. And there are 2 constants, C1 and C2, both positive, clearly. This is the theorem Dalal. It's a really very nice theorem because it deals with general convex bodies, not smoother polytopes. And now a simple approach would be, so you have n points at all. You have n to the power 2 over d plus 1. This is the number of layers. These are all points. So many random points are there. And so in the mean, you would expect n divided by n to the power 2 over d plus 1 points in each layer. In the mean, you have n points, n to the power 2 d plus 1 layers. So this is what you expect. So the number of vertices in each layer should be something like n to the power d minus 1 over d plus 1. And this is precisely the result of Kalke and Quian, only for the first k layers. But they prove this, that this mean value really occurs for the first layers. And the result of Dalal tells us that somehow we expect this in all layers. Clearly, the last layer is maybe a simplex. It's wrong for the last layer, and maybe it's wrong for the first layers. We know that it's wrong for the first layers. If the mother-body K is a polytope, then we know that at the beginning there's a logarithmic behavior. But somewhere in between, all these layers behave like for smooth convex bodies, somehow. Yeah, this is the result of Dalal. Let's do something by the result of Dalal. So I have written ln as the maximum over all x, ln of x. Yeah, this was 0, this is 1, all points here get 2, all points here get 3. I'm looking for the point x with the maximal layer number. This was 3 here. So this is the maximum here. And I take this and put it here by multiplying this inequality or dividing by n to the power 2 or d plus 1. Then we get something like this here. And this tells you the following. So we have 0 here, we have 1 here, we have 2 here, we have 3 here. So if you try to make a bad picture now, I have something like this here. Here we have the value 0, then we have a step 1. So the indicator function is equal to 1 here. And then we have 1 here. And then at a certain set inside here is P2. It gives you the value 2. And then there's value 3. And just to get something like a mountain here. Yeah. Maybe my picture is not the best one, but you get something like a mountain here. It's the sum of indicator function. It starts at 0, then you have a step up to height 1, then up to height 2, up to height 3. And height 3 is in my picture here the highest level. Yeah. If you, the result of Dalal tells you, if you divide your mountain here by n to the power minus 2 over d plus 1, so that each step is not of height 1, but of height n to the power minus 2 over d plus 1. Then you derive in the limit as n tends to infinity by something like a mountain. And the maximal size here, there's a top of a mountain, and the top of the mountain is somewhere between C1 and C2. So this is the right thing here. This is the right normalization. If you think of this convex hull peeling as constructing a mountain, then this is the right normalization that in the limit the mountain converges not to something which is flat or tends to infinity, but gives you a serious mountain. And that's the nice intuition behind the result of Dalal. Yeah? This is the right normalization. And this has been made very precise very recently in the work of Calder and Smart. They proved that this in fact converges improbability to some kind of function or mountain. Yeah, sorry. This is somehow your mountain. H of x. And this converges in probability. And they are using tools which are not from convex geometry, but say from game theory or something like this. So this is a proof which is very hard for me to understand. But at the very end, they say there's a function h of x, which is well defined. And they even can say how this function h of x looks like. It's the unique viscosity solution of a certain partial differential equation. Is from game theory. I do not claim that I understand fully what is behind all these things, and I'm not one of the specialists in partial differential equations, so I can just state this. But the nice thing is they really can prove that there's convergence in probability, so that we start. So this is a huge step in understanding convex hull peeling, in my opinion. Okay, it's still open in my feeling what this function hx really looks like. We have a description in form of a partial differential equation. But say one of the interesting open questions would be for me, is it true? Is it true that this is a concave function? Because this is what one would expect. One would expect you have your convex set k here, and then you have your function, and it would be surprising if the convex hull function looks like that. That this would be very surprising. So one would expect that it looks somehow maybe concave, or maybe some power of it is concave. Yeah, but this would be an interesting question. Can we say something quantitative about this function h? Yeah. And then clearly the second open question, in my opinion, in this field is it true that the result of Kalk and Quian, how the expectation of the number of vertices of this convex hull peeling, they could prove what's going on for the first 10 or 100 convex hull peels layers, but can we say more? Can we say something if, say, k behaves like a logarithm of n or something like this? Or can we say something about all convex hull peels? Okay, so this was the third part of the final part of my talk. Thanks a lot, and I'm waiting for questions.
Yeah, Matthias, I have a question concerning this peeling. So what you do is you peel off the first layer, so to speak. So these are all the extreme points of this random polytope,
Yeah,
right?
yeah, yeah.
Then what you argue is that all the other points just they just thought that they are chosen from this random polytope.
But that's true.
This is true.
There's a conditioning argument. You can condition on this p and 1,
Yes.
and then it's easily to show that the other points are uniformly distributed independently in p and 1.
Okay.
And you can continue this, yeah.
Okay.
Any other questions?
In the convex hull peeling, what about the volume? Is anything known? You also said about volume, to know about the volume of different layers also. Does this approach give something?
As far as I remember, in the result of Kalk and Quian, they also are interested in the volume case, yeah. I just didn't mention that, yeah. But even then, it would be of interest to generalize this to not only the first 10 or 100 layers, but to general layers.
We have a question for the central limit theorem for the simple polytopes. So there you have only the limit going to 0. So is any rate known there?
Sorry, I'm looking.
You went past it. I think.
I'm looking.
Yeah, this one.
This one.
The previous one.
The next one.
Yeah.
Yes. If k is a polytope, yeah.
Yeah, simple. Polytope. Yeah.
So the central limit theorem is known for general polytopes, not only for simple. Yeah, only for the precise variants asymptotics. Yeah.
So what is the rate for that?
And for polytopes, the rate is known. So not the optimal rate. This is known only in the planar case. But if k is a polytope, then we have a rate here. We would like to remove this for general dimensions. We can remove this only in the planar case. But we have a central limit theorem. Yeah.
This is for only F0. What the other cases? If I, that's also. Oh, for all.
Yeah. Yes, I have stated it here only for the vertex case because we can only for the vertices remove the log factor. This was the point. This is only for the vertices. So for example, the planar case, we don't have this for the volume. And I don't see a simple case. Say, if one's identity allows me to start with the expectation of the number of vertices and then a get the expectation of the volume. This is F1's identity I have shown you yesterday. It would be really nice to have something like this for central limit theorems. You have the central limit theorem for the vertex case, and there's a trick to transform it to a central limit theorem for the volume case or the area case in the planar case. We don't have that. So this removing the log factor, this is only true for the vertices, not for the volume or area case. Yeah, but this we have for everything except the intrinsic volumes where we even do not have the expectation.
Also, one other question for the Dalal's theorem, that C1 and C2, for D equals to 1 case, that should be half, right? If you take D equals to 1, then you should have maximum layer is like n by 2.
Yeah, that's true. Yeah.
In that case, H is constant. Is it constant H?
Say it once again. So what is a constant?
The limit H, the H that you have.
Sorry.
That's constant. Is it?
I have never thought about it. Good question. Yeah, it should be easy to make it by hand. Yeah. Is it a const minus 2? B?
So it's in the middle, right? Boundary will still be.
Yeah. I would think so. Yeah.
Yeah, it will not be constant.
I mean, probably at the center, close to the center, it should be a constant, right? But still.
Yeah,
but still you will have concave when it is constant. Probably.
Yeah.
So for even D equals to 1 case, this H is not completed. So you are saying that H to the power alpha is it's not done.
No, I haven't seen this example. Yes, it's a good question. One should have computed this in a one-dimensional case to get a feeling what is going on.
Right.
Yeah, I have never seen this. Yeah, good question. Yeah, maybe one can do it by hand and get a feeling about whether this is a good conjecture or whether this is nonsense from the very beginning. Yeah, you're right.
Thank you.
Okay, any other question? Not, let us thank the speaker.
Thank you.
Matthias, so you will send today's slides as well?
Yes, I will send you the slides. Yeah.
Thanks a lot.
Okay, so see you.
See you. Bye. Thank you. I thought Elizabeth will say in Hindi. In Canada.
In Canada, yes.
Here we will. Okay.